Yes, sir. Thank you.
Okay, Tiang Wei, thank you. Okay, so before we start, just to let you know that our EAC visit for mechanical, mechatronics, and E, okay, will be on next Tuesday and Wednesday. Okay, so I am the person in charge for mechanical department, so I have to cancel the class on Wednesday. Okay, so I think we need to find a replacement class with all of you. And then for last week tutorial for REE Group 3, can we make the tutorial this tomorrow at the same time? REE Group 3. Any class rep over here for REE Group 3? Because last week we have the Hari Raya Haji, so we don't have the tutorial class. And then next week, I will have to cancel the class for EACVC. So we have to replace lah. So okay, yeah. So next tomorrow we have tutorial on 9 a.m. 9 to 10 a.m. for REE Group 3. Okay, so tutorial class started, then we talk about the lecture. Mechanical. I think I have the timetable for mechanical and mechatronics. I'm waiting for next one.
Yes.
Yeah. Checking mapping the timetable because this involves too many classes over here. Okay, can we make the replacement class on Thursday 2 to 4 p.m.? Anyone of you have class? Thursday 2 to 4 p.m.
I think mostly no lah for mechanical.
Yeah, if I refer to your timetable,
yes, sir.
How about RMH and RE? Anyone have class on that time? Thursday 2 to 4 p.m. No objection, Yeah, Tiang Wei, yeah. Thursday 2 to 4. Okay, Tiang Wei, yeah. So should be no problem. Then I will make it on Thursday 2 to 4 p.m. I mean next week. So next Wednesday we do not have class, and then we'll change to Thursday. I will inform the office to make it available in the timetable. Okay. So Monday class, next Monday class there we still have, and this Wednesday class we also still have. Okay, I think that's all I want to inform you. And remember, please make sure you're aware of your own PO attainment. I think all of you receive the PO attainment result for your own, right? So you know that this PO you are weak, which PO you are very good. Okay, you must aware of that. For EAC, they will interview some of you, but I think they will pick randomly. Ayo, Samuel, you have class from 2 to 4. Samuel, may I know what is the class for? 2 to 4. Is that who else have the class with Samuel? EMF, but I can't see it in your timetable. It's just a temporary class or a permanent class?
Permanent, sir.
Permanent, okay. Very difficult to find a time. Okay, how about Monday 4 to 5? Anyone have class Monday 4 to 5? So it means that every Monday we have to make 2 times replacement, 1 hour each time. So we have 2 hour class, 4 to 5. Because our ordinary class is 5 to 6. So I add another hour from 4 to 5. Yeah, RMH okay. RME and REE okay. Okay. Then Samuel, is that okay? Yeah, okay. So we fix to 4 to 5, but not from next week onward, I guess. Okay. It will appear in your timetable. Don't worry. And I will remind you in the Google Classroom again. Okay. Okay, I think that's all. We can start our lecture. Yeah. This is the last part for solar energy. Okay, let's start. Okay, so we start. This chapter is just about the photovoltaic cell. Okay, so of course, first we need to know what is a photovoltaic cell, or we call it as a PV for the short form. Okay, so in general, photovoltaics convert sunlight into electricity using semiconducting material. But normally we use silicon because it's the cheapest. Okay, but of course, other type of semicon also can be used to produce electricity. Okay, as long as they exhibit the photovoltaic effect. I will explain to you what is photovoltaic effect later. Okay, and then this photovoltaic is a solid state device, no moving part. That's why make it so popular. Okay, there's no moving part, and it will convert the sunlight directly into electricity. When you do not have any moving part in the system, it will make low maintenance piece and cheaper and simple. Okay, solid state. It will be very simple, just one plate, and then you can come out with electricity. Okay, and then photovoltaic panel was invented in year 1954 with the efficiency of only 4% and cost about 300 USD per watt. You want to generate the power for 1 watt, you need to pay for 300 USD. And at that time, at that year, I mean around 1950, the commercial power plant, the electricity produced by commercial power plant is just about 50 cents per watt. One is 50 cents, one is 300 US dollar per watt. So there's a huge difference between solar and conventional power plant or commercial power plant. Okay, so in that year, definitely solar will not very popular because they do not have any potential to generate profit. Okay, but at the time of the invention, it's very popular because they come up with a new theory that they can convert the solar energy into the electricity, but they cannot find the application because it's too expensive. No one will pay for it until they found to use it on the satellite. This is the only way you can use the photovoltaic panel, and you are no need to compare with the commercial power plant, because on the satellite you cannot use cable to transfer the energy. You are not able to use a battery. You can use a battery, but the battery will drain very fast, and then you are not able to recharge the battery. So what for you bring the battery if you cannot recharge? So solar energy gives a very good advantage for satellite. Okay, so it means that in that year, solar panel is used only for satellite. And other purposes, other things on the earth, we still use commercial power plant, which is much cheaper than photovoltaic panel. Okay, only satellite. This is the only way why we still use photovoltaic today. If in the year of 1954 we don't have satellite, I think solar panel will not have any future. No one will go and improve the efficiency of solar panel. Okay, because they found the application, so that they try to improve it. Okay, and today the cost is about USD 13 cents. You can see that dropped from 300 USD per watt to 13 cent USD per watt, and with the average efficiency of 12%. Okay, so it's dropped so much because of the technology. Okay, because they see their potential, and all the researchers try to improve the system. And the PV lifespan is about 20 years. And this is very subjective. How you define PV lifespan 20 years? So this one, we need to look on this solar panel degradation and manufacturer warranty. Okay, you see that dark gray, okay, dark gray line going down from 98 to 80. Okay, this is the degradation of the power output from a solar panel. So when you have the brand new solar panel, the output should be near to 100%. Okay, from here you put 98 lah. Okay, and then you drop gradually, maybe around 1 to 2% every year. Okay, and until year 25 is still able to produce a power output of 80% from the rated power. Okay, initially it can generate 100 watt, then now still able to generate 80 watt after 25 years. Okay, it will drop slowly. So in other words, after 50 years, actually my solar panel is still able to use, thus the power output will drop maybe to 50% or maybe 40%. Okay, and you can see that the degradation of power panel actually is a straight line. It do not have a curve. Initially it won't drop so fast and then drop very fast. No, it's almost a straight line. Okay, it constantly drop a little bit by a little bit, because due to the amount of the electron can generate from the semicon will getting lesser and lesser when it become older and older. Okay, so it's something like a linear degradation, we can say. And this light gray line, you can see there's something like a stack. This is the warranty given by the solar panel manufacturer. So they give you the warranty, say that the power output should be more than 90% within the first 10 years. And then it will be more than 80% from 10 to 25 years. This is normally how they give you the warranty. But of course, different company will give you different warranty period. Some of them will give you until 15 years only. Some of them will give you until 25 years. Okay, depends on different company. Okay, and then we talk about energy payback. In this year, 1954, when you use the solar panel or photovoltaic panel, the cost of energy, not the cost of energy, the energy you pay to build the panel is much higher than the energy you can generate from the solar cell for its entire lifespan. Okay, so in terms of energy, it's definitely you cannot break even. You will never break even. You use too much energy to generate a photovoltaic panel, which can generate just a very small amount of energy. You will never have the energy payback break even. But now the energy payback period for rooftop PV, the PV that you put on the rooftop, is just about 4 years for the polycrystalline silicon, which we usually use. This is about 4 years. And then it means that after these 4 years, you still can use the panel for 30 to 40 years. So there's extra energy that we can generate. So they come up with a lot of potential for this photovoltaic panel. Okay. And this is the cost of photovoltaic panel. We'll start from the graph on the left-hand side. Okay, you can see that the title, the price of solar modules declined by 99.6% since 1976. Dropped so much, starting from more than 100 USD. Okay, drop until now, I think it's around 13 cents. Okay, 13 cents USD. But of course, not linear. You can have the slightly stable a bit and then drop. Okay, depends on the technology development, how fast the technology development and how good is the economy at that year. Normally, when the economy better, then you will put more money, more fund to develop a new system or to improve the system. Okay, so you can see that it dropped so fast. And then above here is a cumulative installed solar PV capacity. Okay, now it's more than 100,000 megawatt. Okay, and then if you look on this graph on the right hand side, okay, from 76 USD in 1977 until now 2015 is 0.3 and 2020 is 0.13. Okay, but if do you think that the price will further drop? This is a question. Do you think that it will be cheaper and cheaper? No. Okay, you choose why? No profit. Yes, correct. I believe that the price will not further drop until someone come up with a new technology. Maybe you can improve the efficiency by more than 5%. Okay, so with the same price, you get more power output. So in that case, the cost per unit watt will drop. But the problem is, if we do not have any break even or any new technology, I don't think the price will further drop, because now the price is very, very cheap already, and the company, the photovoltaic panel company, mostly not able to generate too much profit from it. For example, do you heard about this Panasonic will end solar cell production and at its factory in Malaysia and Japan. So Panasonic will no longer produce solar cell in Malaysia and Japan by the end of March 2022. The reason is because they're facing a very strong competition from China manufacturer. Okay, this China manufacturer able to produce the same performance photovoltaic panel at very cheap price, and that Panasonic cannot compete with them. Maybe they still can compete with them, but not able to make profit or huge profit. So they decide to withdraw, don't want to produce solar cell anymore in Malaysia and Japan. Okay, so this is one example of because of the cheap price of photovoltaic panel. Okay, of course, maybe you will increase a bit due to the less manufacturing in the future. Okay, but this one, I'm not there to estimate that. Okay, this is the capacity growth of photovoltaics. You can see that it grows, actually it's an exponential growth of the photovoltaic. Everyone try to use photovoltaic as much as it can. And you can see that the chart, if compared by country, China is always the largest country to build the solar panel. Okay, you can see that China nowadays, they have the accumulated capacity of 254,000 megawatt of solar panel. Okay, and Malaysia is only 1,400 compared to China. Malaysia, I don't know number very less lah compared to them. Mostly it's Europe and developed country, Europe, Japan, China, US. Okay, all of them use a lot of solar energy, and you can see that Vietnam is a new country that contribute a lot in solar panel development. You can see that in year 2016, 17, they even don't have much solar panel, but in year 2020, suddenly they have 16,000, much higher than Malaysia. Okay, so I also wonder whether they not Wikipedia do not have their data, or they just starting to build solar photovoltaic panel extensively. Okay, even in Singapore also try to build their photovoltaic panel system. Okay, but where they want to build, they don't have the land. Anyone know that where Singapore built their photovoltaic power plant, PV power plant? Sea, lake, yes. On the water, yeah, Moody. You said on the water, definitely correct. Sea or lake, not so correct. We cannot build the solar panel on the sea, or we say quite difficult because of the wave and tide. Okay, and also sea water is very corrosive. So I think your solar panel will not tahan lama. So they build it on the dam or reservoir. Okay, first, the water is quite stable. Secondly, it's not really corrosive. The water in the dam is not corrosive. And I can't remember how much they target. They target to generate more. Now already start to build. Okay. Remember, river also quite difficult because river, you have river stream. Unless the river is quite steady, have a very steady flow, then possible. So normally, if you want to build on water, then have to be lake or dam which have no flow, very stable. Okay, and then this is one advantage of is you cannot do for other things for development of building or what. Okay. Secondly, is the water is quite cold if you have the self-cooling system for the solar photovoltaic panel. And we know that photovoltaic system, when you have the cooling, when the temperature of the panel is lower, the efficiency is higher. So according to Singapore, they say if they build the solar panel on the sea, on the dam, okay, on the reservoir, the efficiency of solar panel will increase by 5 to 10%. The output power. With the same panel, you put it on the water and you put it on the ground, the efficiency can improve by 5% if you put it on water. Okay, because it's very cold. You can even maintain at lower than 30 degrees Celsius. But if you build it just like our normal build on the rooftop, I think we can easily reach 50 degrees Celsius. Okay, but in the water, I think you easily maintain at 30 degrees Celsius or lower. Okay, so it's really a good idea lah. Photovoltaics. Maybe some of you have a big land, you can try to build it. Definitely, you can earn the profit lah. Okay, then we talk about how the photovoltaics work. Okay, so photovoltaics is made from semicon. We always heard about silicon, and silicon is type of semicon. So first we look on semicon. Semicon is a process. Okay, this silicon itself is not the semicon, but you need to do something. You need to go through the doping process to make the silicon a semiconductor. So you can see doping is the process of adding impurity to intrinsic semicon to alter their properties. Normally, 3-valent or pentavalent elements are used to dop silicon. Okay, you can see that silicon has 4 electron valence. Okay, we talk about electron valence, then we have to go through what is electron valence. Okay, let's say this is a silicon molecule. Okay, molecule in the middle, we have a neutron and a nucleus. Okay, and then electron will be at the surrounding of the nucleus. Okay, and then you can see that each layer have a first layer. Normally, we have only 2 electrons to make it stable, and starting from second layer, it will have 8 electrons to make it stable. But this silicon have only 4 electrons at the outer layer, outermost cell. Okay, so we call it as a 4 electrons valence. How many number of electrons at the outer cell? This is the number of electrons valence. Electron valence means that the electron can be donated, can be shared. Okay, this electron can be transferred. Unstable because they do not have the very stable structure. Whichever you have the complete 8 number of electrons, it will be very stable. So you cannot donate electron or you cannot accept any electron. But for the last, if you have only 4, then it means that you can accept 4 or you can donate 4, something like this. Okay, this one we call it as a valence electron. So silicon has 4 valence electrons. So valence electrons are the electrons that are located in the outermost cell of an atom. In other words, these are the electrons that can be gained or lost during the chemical reaction. Okay, and the chemical reaction we provide to make this photovoltaic cell is by doping. We add in the phosphorus into the silicon. Phosphorus have only 3 electron valence, and silicon have 4. So now you combine phosphorus and silicon together, it will become. Okay, sorry. Phosphorus has 5 electron valence. Okay, and silicon has 4. So now 4 combined with 5. So what happened? 4 and 4 will become a complete bonding, and you left over 1 electron. Okay, so you can see that the phosphorus atom create an extra electron. If I mix silicon and silicon, the 4 and 4 electron variant will combine, bond, become a very strong covalent bonding. Okay, but now I bond the silicon and phosphorus. Okay, so that now 4 and 5. So you will left over 1. So you have extra 1 electron. So because of this extra 1 electron, we call it N-type silicon. This silicon will act like a negative. You have extra electron, so you have negative charge. Okay, and then another type of the silicon, we also can add in the boron. Boron has only 3 electron valence. So 3 and 4, you combine only got 7. So you left off 1 electron. Okay, so we call it p-type. Left of 1 electron, so we become positive. Okay, you have extra electron, so it means that you become negative. So we have N-type silicon, which we dope in phosphorus, and we have p-type silicon, where we dope in the boron. And now I combine N-type and p-type together to make a photovoltaic panel. Okay, it will become like this: N-type and p-type. So N region on the top, P region on the bottom. Negative part at the top and P part, positive part at the bottom. You cannot about it. If yes, you know that silicon is made from p-type and n-type. So I combine it and then I put the barrier P on the top, which is facing the sunlight, and N on the bottom. Then GG lah, you cannot get any power output. Okay, the negative part must face to the top so that it can get the sunlight to break the bond. Okay, and then now you can see that N region and P region. And the line in between them, this is where N region touch with the P region. So N has extra electron, P has the extra hole. The positive charge we call it hole lah. Actually, it's nothing. It's just missing 1 electron. So if 1 hole and 1 electron, they will combine positive and negative charge. Only on this layer, not on the entire pieces. Only on the layer at where they touch, they will combine into positive and negative charge. Okay, they will make a pair, positive and negative pair. And when the sunlight hit on this positive and negative pair, and the energy from the sunlight is enough to break the bond, then again the electron here will travel through the outer circuit. And when you have electron flow, you have the electricity. Okay, so the concept is you need to have enough sunlight to break the bond of this electron and hole pair. Once you break the bond and you have the circuit connect outside, then you can connect. Okay, but of course, even you break the bond and you do not have circuit connect outside, okay, fine, nothing happened. You will just combine back. You break the bond and then it's go randomly direction, and then you will meet again and combine together again. So you get nothing. You won't say you have too much energy and then you explode or not. What you don't, this thing will not happen. Okay, so first you need to have the circuit so that electron can flow outside and come back to the P region. Okay, so when you flow, you have the electricity. Okay, you can see that some of the sunlight, they break the bond, but the electron may not travel to the port at this side to travel through outside circuit. Then it will recombine. Okay, or some of the case, the sunlight do not have enough energy. Okay, then yes, it's absorbed energy, but it won't break. You need to give enough energy to break the bond. Okay, and then you also notice that N region is much thinner than the P region. You notice the N region and P region. It's not 50 and 50. Normally N region is very thin and P region quite thin. The reason is they need to allow the sunlight to pass through the N region to reach the middle layer between N and P region. If your N region is too thick, so it means that the sunlight will not go through the N region, or very difficult to go through the N region. Okay, so this is the reason why they make N region much thinner than P region. Okay, you can see some of the sunlight will also reflected on the surface, but not go through, not absorbed by the touch. Okay, the concept is quite easy, but actually there's a lot of the parameters that we can study. Okay, for example, how thick is the end result should be optimum. Frankly speaking, I don't know. This one should be very technical. Okay, if you do PhD in solar photovoltaic panel, maybe you can study on this. Okay, what is the optimum thickness for N region? What is optimum thickness for P region? Something like this. Okay. Okay. This talk a bit about energy. Okay, for photon energy. Okay. The solar energy here we call it as the photon energy. For the photon energy smaller than the band gap. Band gap is the minimum energy need to break the bond. Okay, so the energy is not sufficient to promote the electron from the valence band to the conduction band. Valence band is a band that they have last circle of the electron, and then the conduction band is where it can move freely. Okay, the solar cell only use an amount of energy equal to the band gap of the higher electron or photon with lower band gap. Okay, band gap is the minimum energy required to break the bond. Okay, if not enough, you cannot break the bond, you cannot generate electricity. If you supply too much, okay, you still break the bond, but the excessive energy will pass through the photovoltaic panel in form of heat. Okay, so better be exactly the same as what you want. Don't supply too much, don't supply too less. But this is out of our control because the supply is from sunlight. So what we can do is we study the spectrum of the sunlight and design our solar photovoltaic panel which target the band gap correctly. Okay. So how we link this band gap to the solar spectrum? So we look on this equation. Silicon has a band gap of 1.11 eV. EV is a unit for energy, but it's already too small. We cannot use joule. So you can see that 1 EV is actually equivalent to 1.6 times 10 power of negative 19 joule. Joule for us is already very, very small, but now it's 1.6 times 10 power of negative 19 joule. It's very, very small amount of energy because this is just in a molecule. Okay, very small molecule. The energy contained in the photon light is given by EP. Okay, this is energy equal to Hc over delta. H is the Planck constant, C is the speed of light, and delta is the wavelength. Okay, so in other words, you can see H is a constant, C also a constant for light. The top H and C is constant, so the energy totally depends on the wavelength. See that? Planck constant, of course, is a constant, and speed of light for the entire spectrum from X-ray, visible light, UV, all are travel at the same speed. Okay, so to only make them different is only the lambda or the wavelength. Okay, so when the lambda increase, okay, the energy will decrease. So in other words, X-ray have the higher energy and radio wave have the lowest energy. Okay, so for silicon, because of the band gap is 1.11 eV, so we can calculate what is the maximum lambda able to release electron from silicon. Okay, this is how we calculate lambda. So we put in 1.11. This is the energy needed to break the bond or to release the electron from the valence band. Okay, which is equivalent to 1.12 times 10 power of negative 6 meter or 1.12 micrometer. So whichever light have the wavelength of 1.12 micrometer and below should be able to release electron from the photovoltaic panel, silicon photovoltaic panel. Okay, 1.12 micrometer. But if more than that, 1.15, 1.96, then sorry, you are not able to break the bond. You are not able to release electron from silicon solar panel. Okay. Photon wavelength. Okay, this one. Okay, done. Okay, now here we compare different type of semicon material, and these are their band gap: 1.11, 1.24, 2.46, 2.22. Okay, some of them I think GAP is quite normal or quite general to use in the influence solar cell and also CDD. I can't remember what's full name. Okay, so some of them are quite common used in photovoltaic material, but you can see that all of them have the different band gap. So in other words, each layer of the semiconductor material can target different wavelength. Okay, so this they come up with a multi-junction solar photovoltaic panel. Multi-junction means that they have a few layers of the photovoltaic panel. Photovoltaics. Okay, each layer will target on different wavelength of sunlight. In that method, they're able to improve the efficiency up to I think 36 or 38%. Okay, because if I have only one panel, which is a silicon polycrystalline panel, it's only target on one single wavelength, which is 1.12 micrometer and below. Okay, but the rest I cannot do anything. Okay, it will be either wasted or it will convert to heat. But now I can make a few layers, maybe 3 layers. One layer of silicon, one layer of GE, and one layer of Canadian telluride. Okay, CDT. So each layer target different wavelength. So is that a good idea? Each layer I have the different amount of energy. Okay, so this is the best idea, but the cost is still too expensive to do that. Although you can achieve the efficiency of 36%, but I don't know how many times the cost is expensive compared to the conventional solar panel. Okay, so until now it's still in the research stage, but not really commercialized. Again, this is a look on the solar irradiance spectrum. Okay, this is a sunlight spectrum. You can see that we have the UV light. Oh, actually already not in here because normally actually will not reach the sun, the Earth's surface. It will be filtered by the atmosphere very fast. Don't have. So we start from UV, solar, visible light, thermal radiation, and infrared. And 1.12 micrometer is around here. Okay, so whichever we have solar, we have infrared, we have thermal radiation. Okay, all of this able to generate energy or generate electron from the photovoltaic panel. And UV also the same thing. It is 1.12 and below. It have more energy. But of course, you use UV to generate electron from the photovoltaic panel. It's actually you generate a lot of heat. Okay, because remember that the excessive energy will change to heat. So end up you increase the temperature of the solar panel and you reduce the efficiency of the panel. Okay, so the best is target exactly 1.12, but it's not what we can control, of course. Okay, and this is the photovoltaic value change. We start from the polysilicon, and we make a purification through a chemical process to get the pure silicon, and we can make it as a wafer. Okay, and do the casting and cutting to the shape that we want. And then after surface treatment, we can make it polished and shining like this. We call it a solar cell. And then we combine all the solar cells into one, we can get a solar module. Normally what we bought in the market is actually solar module. Okay, something like one plate of solar panel. Okay, and then we install all these solar modules together. We call it as a solar system. This is the PV value change. Okay, but normally we will see solar module. Normally we will stop in this part, solar module. Okay. Then similar, this one, cell module and array, similar thing. Okay, this is a family tree of photovoltaic system. So in general, we can divide into 2 types. Photovoltaic system are no longer module, it means that a complete system. So we can divide into 2 types, grid connected and off grid. Grid connected means that you connect your solar system to grid, maybe to TNB grid, to DNB substation, something like this. Okay, so grid connected, we have direct feed, indirect feed, and indirect feed with energy storage system. Direct feed is which whatever you generate 100 kilowatt, or you will connect to the grid. Okay, this one is normally for commercial lah. I have one solar farm, and which whatever I generate, I will sell to DNB. And then we have indirect feed. This is normally used in household. I have the solar panel on my rooftop. I use the solar energy first, and then the leftover I can sell to the grid, then sell to the DNB. This one we call as the indirect feed. The next one is the indirect feed with energy storage system. You have one energy storage system, which is battery. Maybe you use part of it, you store part of it, and then once you fully charge your battery, you only sell to the DNB, sell to the grid. Okay, so you only have 3 different types here lah. Of course, direct feed, we don't need the battery. We don't have the direct feed with the energy storage system. We not really need that, because we will sell everything to the grid. And then the next one is the off-grid. Off-grid, we have the AC standalone. AC is mean alternate current. So it means that the power generated from the photovoltaics definitely is DC, direct current. So you need to use the inverter to convert to AC. But this is a standalone. It will not connect to any grid. Normally in the rural area, maybe just to power a sensor, to power a motor or something like this. Okay, the next one is a DC standalone, similar, but we do not need the inverter. We just use it as it is. Okay, we generate from the solar panel, and we use it, the DC current from solar panel. But of course, you may need to regulate the current, okay, and voltage. Maybe to charge your handphone, you need 5 watt, something like this. To charge your car, you need 12 volt or 24 watt. Okay, and then the next one is a hybrid, where we combine photovoltaic panel with the diesel genset, because normally when you have daytime, you have solar, but nighttime you don't have. So you combine with the diesel generator set, and then you can supply the energy for 24 hours. And then same thing, PV plus V, also the same thing. Mostly at night, you will have the stronger V. Okay, this is the idea. Okay, this is a sample of the off-grid photovoltaic system. So we start from solar panel. Okay, this is as usual, we put it on our house lah. So we put the solar panel on the rooftop. Of course, face to the direction of the sun. And if you look on the photo, it seems like opposite to the direction of the sun. But actually, we have to face to the direction of the sun. Do you notice that a lot of household, they build the solar panel on the rooftop, but they only build on one side, but not on both sides. Okay, because one side is facing the sun, of course, another side is not facing the sun, most of the case. Okay, so normally they'll build on one side, but of course, you want to build on both sides also can, but the return of investment or break even year will be longer. Okay. Okay, after the solar charge controller, we need after the solar panel, it connect to the solar charge controller. Remember that solar panel will generate the current according to the solar irradiance. The more the solar irradiance, the higher the solar irradiance, the higher the current output. And remember that battery, how you charge your battery, your handphone? You need to supply the consistent or constant current and voltage, correct? To make sure that you have the longer lifespan. Okay, so we have the adapter. Normally, it will help you to regulate the voltage and current. But for this system, we need a charge controller. So the charge controller will help you to control the charge, to control the voltage output and current output from the panel, so that you can extend the life of the battery. Of course, you say you want to save money for solar charge controller. Yes, you still can do that. You still able to charge your battery, but your battery life will be much shorter. Okay, that's why we need the solar charge controller. Okay, after the solar charge controller regulate the current and voltage, you pass to the battery, and now you can use the energy from battery for the DC load. Maybe for handphone. Normally in our household, most of the power supply is AC lah. Okay, but you see if you ever have the adapter, then there's a DC. Okay, do you notice that we actually supply DC load from battery? Can we supply DC load? Sorry, can you supply the DC directly from a solar panel? Yes, you can do that. But again, the power is not stable. Sometimes high, sometimes low. So it may break your system. Okay, or devices that connect to this solar panel. That's why we need a battery. Battery always able to supply a consistent power output to your system. Okay, and then after the battery, the leftover you also can pass through to the inverter. Inverter will convert the DC to AC, direct current to alternate current, and you can use it for AC load. But most of our design in Malaysia, we don't have the supply from battery to the DC load, because most of us will not use a DC load in our house. Everything will be AC load. Okay, so it means that directly from battery to the inverter and AC load. This one is the photovoltaic system with the battery. But if the system is connected to the grid, yeah, for example, this one, do you think that you still need a battery? Normally, we don't need battery because we generate power. If extra, we sell to TNB. If not enough, we buy from TNB. We not really need to keep the energy at our own. Unless the rate you sell to TNB and you buy from TNB is different. Then we already need to stop. Let's say I sell to TNB is 20 cents and I buy from TNB is 40 cents. So what happened? Of course, I want to store some of my energy because my energy is quite cheap and you buy from TNB will be very expensive. Okay, so in that case, you may consider to have the battery. But in Malaysia, the rate you sell to TNB and the rate you buy from the grid is actually the same. So there's no point to build a battery at your home. It incurs extra cost lah, extra maintenance lah, and the maintenance of the battery exposure or whatever. Okay, so it depends on the country lah. I don't know which country you sell to the grid is cheaper and you buy from the grid is very expensive. At that case, you need the battery. Okay, so battery is optional. And do you notice that for this system, grid connected photovoltaic system, they don't have the charge controller. They have solar module direct to the inverter. Don't have the battery, don't have the charge controller. So actually we need the charge controller only when we have the battery. It's to protect the battery. But for this case, the inverter can act as a charge controller as well. The inverter has the capability to regulate the voltage and current. Okay, so regulate the voltage to 220 watt and then it can supply it to the other devices in the home and then connect to the grid. It should be much simpler. You not even need the battery and the charge controller. Okay, so think wisely lah when you design your system, whether you need the charge controller, whether you need the battery, whether you need the inverter. Okay. Okay, I think this one I explained before. Said that. So you can go and have a look lah. So what kind of the target they have, and then what kind of policy they have, what kind of project left over or quota. Okay, you can have a look on this. So now we have the net energy metering 3.0 lah. Okay, as I explained to you in the first chapter. Okay. Okay, this is the example of the application for photovoltaics. You can make it as a solar carport. Okay, because in the carport you need to build the roof. Why don't you use the solar panel to build the roof? So same thing, you save material and at the same time you still can generate electricity. Okay, and then this one is a rooftop mount. Okay, they mount all the solar panel on the rooftop. Okay, you can see that they make it on two parts, both sides. So in this case, why they make it two part? Maybe the sunlight is come from east to west. Okay, so it means that the sunlight move from maybe east from the bottom and west to the other side. So we can absorb all sunlight. But if east from the left and west to the right, then this solar panel definitely will not be so effective. You can see if the sunlight comes from the right hand side, only 50% of the panel will receive sunlight. The rest will not able to receive. Okay, so direction very important. So when you build the solar panel, of course you are not able to change the direction, the slope of your house roof. You cannot change it. Oh, I want to make it face to the sunlight, then I change the direction of the rooftop. This one we cannot do anything now. Okay, so we need to calculate whether is viable or is feasible to build the solar panel on both sides of the rooftop. Okay. Okay, and then this one is a ground mounted. You put it on the ground. Okay. You can see there is always face to one direction only. Okay, and then this is a project on the IKEA rooftop at Johor, IKEA Johor. So they put a lot of solar panel on the rooftop. And this is a UTM campus in Samara, I guess. KL lah, UTM campus KL. You can see that what they make. All is a solar photovoltaic panel. And total quantity of photovoltaic panel is 34,000 units. And total is 10 megawatt. Location is 50 acre of car park. And it's actually funded by RMK11, grant from government. Okay, project cost about 50 million. And this is a 21 years contract under Photon tariff setup. But now we don't have already, as I told you that the quota already been fully used. And estimate energy saving 13.5 gigawatt hour per year. Okay, and estimate income about 150,000 per year. Okay, quite attractive, right? If you able to get the Photon tariff at that year, very attractive. Estimate income on profit sharing of 10% is about okay, this profit sharing is something like this. Normally, the company that built the solar panel for you, they may sponsor you something. Some of them even zero capex. Zero capex means that you don't need to pay anything. They build the panel for you, they give you the material, and you just need to give them the space. Okay, so you provide space, they provide the material and installation, and you share the profit. Okay, so this is actually a good idea, but this one I think seems like profit sharing is only about 10%. It's a good idea. Maybe one day we will build in IUC. Okay, then we talk about family tree of PV type. We have different type of PV. Then the most famous one is a crystallized silicon cell. Okay, this is a widely used because of the high efficiency and low cost. Remember that silicon is something like widely available everywhere. Okay, it's extract from the sandstone normally. So as long as your country has many sands, then you can make your silicon solar panel, something like this. Okay, so this crystallized silicon cell also divided into two types: monocrystalline cell or highly crystallized cell. And all the molecules arranged nicely. And polycrystalline cell is crystalline by part. That's why we call it polycrystalline. So polycrystalline should be lower efficiency because it is actually a crystalline by part, not 100%. Okay, maybe I show you like this. Yeah, monocrystalline. You can see that all the molecules arranged nicely for the entire panel. Not entire panel, like entire photo PV cell. And this polycrystalline, you can see that they actually crystalline, yes, but they have a few region, not completely crystalline. They crystalline part by part. So that if the same amount of area, monocrystalline will have more molecule than polycrystalline. So in that case, it will make it higher efficiency. Okay. Yes, yes, correct. The 10 megawatt is just a panel output times the number of panel. That's correct. And remember that you will not never get 10 megawatt output. 10 megawatt is called rated output of the system. Okay, it means that maximum possible output of the system at the standard test condition. Of course, I don't think you can get that power output just because of the temperature of the operating, normally much higher than 25%. Sorry, much higher than 25 degrees Celsius, which is the standard test condition. And then the solar irradiance, at standard test condition is 1000 watt per square meter. But how many hours you can get 1000 watt per square meter in one day? In the morning and in the evening, definitely impossible. Maybe just a 1 or 2 hour, you can get 1000 watt per square meter. Okay, so 10 megawatt is called rated power, or maybe just peak power. Yes, the installation capacity is used that as the rating. So they say 10 megawatt, it means that they just give you the maximum output. But of course, due to the capacity factor, then it will be very low. Okay, that's why 10 megawatt solar power farm and 10 megawatt hydro power system is totally different. Don't say that, oh, this one 10 megawatt and this one 10 megawatt totally the same. No, 10 megawatt solar and 10 megawatt hydro is totally different. I mean, they told you about the power plant. They say 10 megawatt power plant, hydro power plant, and 10 megawatt solar power plant. The total energy you can generate in 1 year is totally different story. Okay. Okay. Other than monocrystalline and polycrystalline, we still have amorphous. Amorphous is something like this, not very crystalline. Okay. So in other words, the efficiency will even worse because they are not aligned properly. So that per unit area, they will have less molecule or less atom to release electron. Okay, so end of it, monocrystalline have the highest efficiency and amorphous have the lowest efficiency. And polycrystalline have the highest cost per power output, something like this. So we can say that polycrystalline is the cheapest. Cheapest not in terms of price, cheapest in terms of energy. Okay, so you can see that most of the system, they will use polycrystalline. They will use monocrystalline only when your space is very limited. I want to generate many output. I need a huge output, but my space is very limited. So of course, you need to use the best monocrystalline or best power system. For example, I remember that Apple built their headquarters at somewhere, and then they want to make use of photovoltaics to power the entire building. And then they use monocrystalline. They want the best efficiency. They want to have the best output. They don't care about the price. Then you can use monocrystalline. Okay, so it depends on what you have. But for cost effective, definitely we use polycrystalline. Okay, so you look on this. Okay, amorphous no longer categorized as crystalline because definitely not crystalline. Okay, but actually we can combine amorphous and monocrystalline and call it as a hybrid HIT cell. I think Panasonic have this kind of cell, hybrid HIT, and it can improve the efficiency by 2 to 3%. Maybe monocrystalline will give you efficiency of 15%. This hybrid HIT will give you the efficiency of maybe 18%. It means they have 2 layers. First layer is monocrystalline, and then bottom layer is amorphous. Okay, so the power plant capacity is typically normally they talk about power plant capacity, talk about the rated power. So in terms of what? Okay, unless they talk about the annual output power, then we talk about megawatt hour. Okay, I think we stop here. 6 p.m. already. Okay, Chongyi, is that okay? So normally they talk about power plant capacity, they talk about the rated power. So 10 megawatt or 1000 megawatt something like this. Okay, any other question?
Yeah, sir. I have a question in regarding the getting the electricity generation of the solar panel lah.
Okay.
So the formula I found online it just said like the area multiplied by the solar panel efficiency multiplied by the solar hour and then multiplied by the performance ratio lah.
Okay.
So if I, for example, my project lah, I say like I have a 2.5 million panels.
Okay.
So like because my one rating of the capacity is 300 megawatt lah. So I get like roughly
Okay. Let's say you have one solar panel. You put it 300 watt one panel. So it means that at standard test condition, the panel will give you 300 watt.
Yeah.
But the problem is we do not always have the same amount of solar irradiance, sometimes lower, sometimes higher. So normally we will calculate according to the peak sun hour. You heard about this peak sun hour?
Not yet.
So it means that maybe 1 hour of solar irradiance of 1,000 watt per square meter, we call it as a 1 peak sun hour.
Okay.
So let's say the solar irradiance is only 200 200 watt per square meter for 1 hour. We assume that it's just only 0.2 peak sun hour.
Okay.
So in that case, they will calculate how many peak sun hour you have for 1 day. And then they can estimate how much total accumulated energy output for 1 day.
Okay.
Actually, you can refer to the lecture note. I think the end of this chapter, I will teach you how to calculate this.
Okay, thank you, sir.
Is there any rush? Very rush? You need to get the answer because it's quite long.
Because it's just like for the financial part lah. Because if I look up the solar panel lah, it says 120 watt, and then it says like it's guaranteed to have after 20 years still have 80% efficiency.
Okay, not 80% efficiency, 80% rendered power.
Yeah. So then if I use that's how the energy formula I mentioned to get the kilowatt hour, I get the annual total power generation, which is roughly mega 780,000 gigawatt hour for the 2.5 million panel. And then I degrade it by 1% annually. Is that considered reasonable for my power output?
Okay, if you calculate the power output like this, what is the capacity factor?
Capacity, which is the power ratio, right?
Capacity factor is the actual amount of energy you generate divided by the maximum possible amount of energy you're able to generate, which is mean by capacity times time only. How much is the capacity?
300 megawatt.
300 megawatt times 24 times 365, then you get the maximum capacity.
300
megawatt times 24 hour times 365 days. So it means that you get the total energy you can generate in 1 year maximum in terms of watt hour.
Okay, so if I get the actual one is less than my total one, that means it's reasonable, right?
No. Of course, it must be less than that, but it's just about around 20% of the maximum, supposedly, or less than 20%.
Slightly more.
Okay.
Slightly more than 20%.
Oh, then it should be quite reasonable. Maybe your solar panel is quite high efficient or what, I don't know. Like quite reasonable. Normally it's just around 20% capacity factor.
Okay.
Because some of the, how should I say, you have different information and then you count differently. You count from efficiency or you count from peak sun hour. But finally you will get similar answer. But I don't know what kind of information you have.
But then if the difference is like 250 trillion in difference of the two, because the peak one is 525 trillion, the one I got is like 750 trillion.
Sorry, I don't understand.
Okay, never mind.
Okay, wait, I talk to the others first. Okay, by the way, others, if you do not have question, then you can leave first lah. So let me talk to Munjun.
Yep.
And the rest, if you want to leave, you can leave first lah. Okay. Okay, Munjun, you can continue. Okay, thank you. Yeah, Munjun, continue.
So my peak hour of the 20% is around 525 trillion.
Okay,
And then based on the energy formula I calculated for the other one, which is I get like 780 trillion.
Okay, how many percent different? Because the value too big already.
Okay, butterfly. 50% difference.
50 or 50?
50.
So it means that your output is much higher than 20%, 30% around.
Yeah, roughly there.
How much is the efficiency?
I thought the efficiency I follow the manufacturer given, which is 17% efficiency.
17%, okay, quite normal.
Mm-hmm.
Okay, explain to me how you calculate 17.
Do you want me to show you the formula, sir? I show you my screen better, so like easier for me.
Oh, okay, can, sure.
Wait, hello, Google, why are you lagging?
I can hear you.
Hello.
Yes, Munjun, I can hear you.
Hello, sir, are you still there? I think my computer.
Yeah. I stay here. Yeah. Can you hear me? Yeah, Jinwei, yes, you can stay back if you want to learn something. No problem. For those who want to know more about solar, you can just stay back.
Sir, I think my computer crashed. Wait a while.
Yeah, okay, yeah. Or anyone have any question about your assignment, you also can ask here. We are waiting for Mundu. Ken Long, what is actually the title of your project? Is that solar? Definitely not. Okay, rated power, normally the annual output capacity is just close to 20% of the rated power. So it means that your system actually is 10 megawatt, but the average power output should be around 2 megawatt only if you divide by 24 hours. Okay, because as travel, you cannot get any sunlight. Morning and evening, you also cannot get a very good power output. Okay, but try not to just multiply 0.2 lah. Do the proper calculation.
Okay, so sir, I follow this formula lah. This global formula given.
Okay.
The PR I'm using 0.5. The R, this one I follow the manufacturer given one, which is the 17% here. And then the area I use the 2.5 million panel multiplied by the given specification here.
What's the H?
The H I use 12 hours.
Okay, why 12 hours?
Because I follow my friends, they do the other part for the literature review on the Malaysia part. It says like roughly 12 hours. So I guess is that the problem there, lor?
So
It
do
should
you
not be
think?
12 hours, lor.
Okay, your assumption is the solar energy is always 1,000 watt per square meter. Do you think it's possible? Because you see,
No.
your equation is area times what is R? Efficiency.
Efficiency of the
Area
PV.
time efficiency times H time PR. What's PR?
PR is the performance ratio. They say like assume for losses and stuff.
Area times efficiency times hour. Then where is the solar irradiant?
It's not factored in.
Then where is your
The H is this one, the solar irradiant, the H part.
yeah. Then okay, Then how you use 12?
Oh yeah, I guess I misunderstood the formula.
Yeah. Something missing in the formula. Maybe you can refer to the lecture note lah.
Yeah, okay. I'll refer to the lecture note.
And then when is submission date lah?
Wait, double confirm first.
I think we able to complete this chapter by this week, I guess.
August 9th. So like another 2 weeks off.
Okay, I think you wait until we complete the chapter first lah. Then you should have better understanding on that.
Okay. All right. Thank you, sir.
Okay, thank you. Bye. Okay, thank you everyone, and see you on Wednesday. Okay, bye bye.